Alright, so let's take a look at some problems to help us prepare for skill 3, which is relations and functions. So before we jump in and start doing some specific problems, let's think about definitions and think about some preliminary things. In high school mathematics, most of our studies is about sets, and a set is a specified collection of objects, whether we're interested in the solution set or the domain set, the range set, a set of ordered pairs. We're consistently interested in sets, and for this class it's really sets of numbers. So a set is any specified collection of objects, and for us these objects are numbers. So we've seen sets of numbers before as we've gone through our math classes from elementary school all the way through high school. You may have started out with the set of natural numbers, numbers that are also sometimes called counting numbers, 1, 2, 3, 4, 5, and so on. Okay, the set of whole numbers is the set of natural numbers, but including 0, 1, 2, 3, 4, and so on. The set of integers is the set of whole numbers and their opposites. So you're now including negative values. So -3, -2, -1, 0, 1, 2, and that pattern continues. The set of rational numbers, it becomes a little bit harder to write it, so they use set builder notation, and you express rational numbers, that idea ratio, are numbers that are fractions, where the numerator and denominator are from the set of integers, with the restriction that you can't have a 0 in the denominator. So of all these infinite set of integers, pick a number for the numerator, pick a number for the denominator. It's just that denominator cannot be 0. Irrational numbers are real numbers that cannot be written as a ratio of integers. Irrational numbers, pi, square root of 2, e, so forth. They have a decimal representation, a decimal that goes on forever with no kind of a repeating pattern. If you have a rational number like 1/3 and you try to convert it to a decimal number, we see that 0.3, that they'll put a bar over it oftentimes to indicate that 3 is going on forever. With irrational numbers, it goes on forever, but there's no kind of a pattern. You can't put a bar over it. The pi, 3.14159, and it just keeps going, and there's not any kind of a repeating pattern. The set of real numbers, maybe your first exposure to it is when they drew a number line. They may not have called it the real number line, but that's what it was. And real numbers consist of rational numbers and irrational numbers. And it's either or. A number cannot be both rational and irrational. But the set of rationals in union with the set of irrational numbers makes up the set of real numbers. And then finally, we have looked at in detail in this course the set of complex numbers, numbers that can be written in the form of a plus bi, where this number I was referred to as the imaginary unit, and we defined it to be the square root of -1. So you've built the set of numbers that you've studied in high school, in your mathematics from elementary school all the way through high school. We're interested in eventually getting to functions. The title of this skill set is Relations and Functions. A relation is a set of ordered pairs. So it's not just any old set of numbers. Every element in the set is a pair of numbers. And we typically refer to the first number in the pair as the x-coordinate and the second as the y-coordinate for a set of ordered pairs. When you have a relation like this, we often are interested in the domain and range of this relation. The domain is a set of x's. It's a set of first numbers. Now you can see that the domain is not ordered pairs. There's not an x and y. It's just the collection of x's. And if you're writing a finite set, if you have two numbers that appear here, when I'm writing the domain, once you're in, you're in. I don't have to repeat that element of 5 twice. That's not. I haven't made any kind of a typo, any kind of a mistake here. I've listed 5 as being a member of the domain, and once you're in, you're in. You don't have to repeat it if you see that value more than once. The range is a set of y values. You can see 2, 1/2, 4, and 1. So we're interested in a specific type of a relation that achieves the. I like to think of it that if a relation achieves the title, if it gets promoted to a title of a function. A function is a relation for which every element in the domain is associated with exactly one element in the range. Every input will have exactly one output. And we looked at some elementary examples of that when we learned this definition, and hopefully you can recall that. The function notation, when we were in Algebra 1 and Algebra 2, or wherever it was that we were first introduced to function notation, was a little bit of a jolt. Before, when you first learn algebra, when numbers are written next to each other without any kind of symbol in between there, multiplication is implied. But here, when we have the f and x written next to each other and this x in parentheses, you have to realize the context of the problem and recognize that this does not imply multiplication, that this is function notation. It is convenient when you're learning functions and stuff to sometimes think of a function as a black box where you have from the domain set a set of x's that you refer to as input into the function. The function is some kind of a rule. For the function I have written here, it takes any element from the domain and it adds 3 numbers together. The first number it gets by squaring the input, the second number it gets by 5 times the input, and the third term here is just constantly 6. So whatever number you plug in there, you can do that arithmetic and get an output. And I claim for each number that you have an input, there'll be exactly one output. You won't plug in 3 and get 2 possible outputs, a 5 or a 4, you know. And that's the important thing, and that's why we can apply these functions to so many real-world problems. You know, if you're old school and I don't know, DVD stores and stuff, renting movies and stuff is becoming a thing of the past with the internet. But if you still go to Family Video or someplace like that to rent some movies, or Redbox in front of these things, for every input there's exactly one output. For if you rent the Green Mile, then it's going to be, you know, maybe $2 a night. If the person behind you in line rents out the same movie, they expect the same price. So every input has the same output, not different outputs. It shouldn't, unless you had a late fee or something like that associated with it. But your cost of something, whether you're riding in a taxi cab, whether you're paying gas at the gas pump, just because you're second in line, should mean that you're paying the same price per gallon as the person that's right in front of you. So oftentimes with equations and stuff, we're interested in mathematics all the time of a picture. When we're doing word problems, we're constantly it's suggested that we draw pictures, and that pictures often help us understand things a little bit better. And with equations, the type of picture that you want is referred to as a graph. So a graph, how we graph things in the rectangular coordinate system, is the numbers in the domain. We write a number line that represents the x-axis. We have a perpendicular to the x-axis, another real number line that we call the y-axis, and in two-dimensional space we use x comma y to locate a point from a point that's referred to as the origin, from 0, 0. So every graph is just a collection of x and y's, a collection of ordered pairs. So therefore, if a relation is an ordered pair, every graph is definitely a relation. Well, when we're trying to determine whether this relation is a function or not, it's a very powerful tool to have that picture and to look at it, because we have a test to determine if a relation is a function or not that's referred to as a vertical line test. If you have a graph that fails a vertical line test, that means that there exists some type of a vertical line, at least one, that intersects your graph in more than one place. So here I found a vertical line that intersects my graph in 3 locations. This is definitely a relation but not a function. Now even over here I might be able to, here's a vertical line where you're like, hey, it's only crossed once. Well, all you have to do is find one vertical line where it crosses it more than once, and we say it fails that test and it fails to be a function. It fails the vertical line test. Now over here, it looks like I have some cubing function that I've sketched, and you can't find, no matter how hard you search, no matter how many vertical lines you find, you can only find a vertical line that's intersecting the graph in just one place, or maybe it could be that it intersects it not at all. You have maybe a square root function where you have a vertical line over here that doesn't intersect the graph at all, but remember, it fails if it intersects the graph more than once. All right. The domain is something that we spent considerable amount of time looking at. If you have the domain given an equation, or if you have the domain given a set of ordered pairs where it's just writing down the x's, or a graph. So looking at the graph to find the domain, looking at an equation to find the domain, those are important things to understand. So the domain of a function is a set of all real numbers for which the function is defined. We had, so your default answer whenever they say, hey, what's the domain of this function, is always going to be the set of all real numbers. But then you have to look closer inspection if you have an equation. If you have variables in a denominator, then there exists a possibility that some of those values of x may cause division by 0, and you can't allow that to happen. If you have 1 divided by 0, then you won't get you won't get an output. There's no corresponding y value, that we say that this is undefined. So any x that causes division by 0, if you have 1 over x minus 2, then I can plug in any x that you'd like, any real number, with the exception of positive 2, because if I let 2 be in the domain, then what would I have as a y value, as the output of the function, because 2 minus 2 is 0, and 1 divided by 0 is undefined. So if you have division by 0, and if you have the square root of a real number, you can't take the square. We're working in the set of real numbers, not complex numbers now when I'm talking about domains of functions, and you can't take the square root of a negative value and still be in the set of real numbers. We also saw just recently with logarithms that we can't take the log of 0, or we can't take the log of a negative number. So if you look at the square root of x, you can take the square root of 0. So our domain here was non-negative real numbers, 0 or positive. Well, we can't take the log of 0, so we have to exclude 0. So the domains look very similar, but remember that bracket includes 0, where this parenthesis, or oftentimes I say an open parenthesis, excludes that endpoint of 0. So here, let's jump in and take a look at some problems. Now here, it's asking us to identify which of the following equations defines y as a function of x. So our answer on each of these is going to be yes or no. Yes, it's a function, or no, it's not a function. And we looked at it. We came up with some basic rules of thumbs to help us quickly answer this. If I see an absolute value symbol around a y variable, I know that does not define a function. If I had the absolute value around x, that's okay. If oftentimes we think about the graph, because the vertical line test is so powerful, the absolute value of x looks like a V that's opening upward or downward, and that passes a vertical line test. If you think about an absolute value of y, then that V is turned on its side, so it either opens to the left or to the right, and here it clearly fails the vertical line test. So when we have an equation that has an absolute value symbols around a y variable, there's no way that that's going to be a function. So my answer for part A is no, that is not a function. When I have some type of an expression here, like a polynomial expression, I need to look at the exponent on y and determine whether it's an even exponent or an odd exponent. If I have an even exponent, then to solve this equation for y, I would take the absolute value, and since I'm taking the square roots of this, this symbol is the principal square root, but to satisfy the equation, positive or negative would work, you have to put a plus or minus symbol. So whenever you see a plus or minus symbol, your output is not unique. You're saying there's a possibility for an input, for an x value, that there's two y values. If we have that y squared is equal to 4, then for this value of x, if we're letting x be 4, y could be -2, but it could also be +2. So here 4 is related to -2, but 4 is also related to +2. That's not a function. And so whenever you see this plus or minus symbol, just like whenever you see absolute value symbol around y, if you see a plus or minus symbol in an equation, it's not going to be a function. Well, that plus or minus symbol is going to come from, if you look at the step above, if you have an even exponent on the y variable. So like right here in C, I see that this is an even number on y, and I immediately know that on C that this is not a function. Well, let's return to B. Since that's odd, I'm okay. If we have an odd function, an odd exponent, excuse me. If we have that y cubed is equal to x, when we take the cube root of each side, then the cube root is defined for negative values. We don't put a plus or minus symbol in there, and we're fine as far as being a function. So yes, this is a function, and it's basically boils down to our rule of thumb that when you have an odd exponent on that y variable, and remember that the y variable doesn't have absolute value symbols around it, then yes, it is a function. We look here, y equals -3. The graph of that's a horizontal line, and even though it's not written, this is implied y to the first power, and that 1 is an odd number, so it's not contradicting our previous statements. And this y equals -3, here's my y-axis, my x-axis, the line y equals -3 is the graph is a horizontal line, because every point on here, they have different values for x, but every point has one thing in common. They all have a y-coordinate of -3. You could rewrite this as 0x minus 3. You can see that the slope of a horizontal line is 0. But we typically, 0 times anything is just 0. So we usually don't write it in slope-intercept form. We just usually write y equals -3. All right, now in E, in letter E, we have just a variable x. If we solve for x, we've got this -12 divided by 5. So if you go to graph that, it's a vertical line, okay? One thing that all of these points on this line have in common, all of the x's are the same. And in this case, if it was -12/5, well, that fails the vertical line test. We can find a vertical line that intersects us more than once, just lie a vertical line right on top of it, and it intersects it infinitely many times. So, it's the worst case scenario as far as functions go. A vertical line fails the vertical line test miserably. It intersects it everywhere. All you need to do is to have it intersect in more than one place. Well, infinitely many times is definitely more than one. All right, so this guy is no, that this is not a function. And if we look at this f, we see that y plus 3 quantity squared, if you were to FOIL that out, if you were to multiply that out, then because this exponent is 2 and y is eventually going to be squared, just like, where did it go? Just like here in C, you have an even exponent on the variable y, we have an even exponent on the variable y, this is not going to be a function. If you go to graph that, that it's a parabola, but that parabola is opening to the left. If you have a parabola that opens up or down, just like my picture before of the absolute value, that's going to pass the vertical line test. But if you have a parabola that opens to the left or to the right, then it's going to fail the vertical line test. Alright, so let's take a look now that it's wanting us to state the domain of each of these functions. Now, it's not using function notation, it's using old school, it's just using the variable y. We have seen that when you're starting to look at functions in the domain of functions, that oftentimes they will not use y, but they will use f of x. So your function may be written using function notation, or it may be written just with a y variable, and that shouldn't bother us. So here we have a square root symbol. We know that we can't take the square root of a negative value. So this 3x minus 6, I don't know what number it's going to represent. It depends upon the value of x, but I know that this number has to be a number that is 0 or positive. It has to be a number that's greater than or equal to 0. So if we solve this inequality, we'll be able to figure out what the domain is. So you add 6 to both sides, and you have that 3x is greater than or equal to 6, and then divide by a positive 3, and when you divide or multiply by positive values, you don't change the direction of the arrow, and 6 divided by 3 is 2. I like to keep my variables on the left because if I draw a picture on a number line, if say this is 0 and this is 1 and 2 and 3 and so forth, and over here negative numbers, what I'm interested in is that the equal portion here at 2 is going to be a solid point, and since the arrow is pointing to the smaller number, it's saying that x is larger, x is greater than or equal to these. I'm interested in this set of numbers, all of the numbers that are greater than or equal to positive 2. And we typically represent that using interval notation. So, and we often use just the letter D for domain. Since that is a solid point that's included in my set, I use a bracket, and this arrow that's shaded, it's going out to the right, isn't a number, but it represents an abstract concept, the idea that it's going on forever, and we use this symbol positive infinity to represent that. So the domain for this in interval notation is this set from 2 to infinity, where 2 is included in our set. Let's take a look at another example. Well, again, we have they're asking us to find the domain. The domain is a set of all real numbers for which the values the function is defined. Since we have variables in the denominator, there exists a possibility that we could have division by 0 for certain values of x. Now, in the denominator here, it's a polynomial, and when it's written in this form, I can't necessarily look at that and just immediately see what numbers would cause me problems, what numbers would cause division by 0. So I come over and I do some scratch work, and I say, well, this x squared minus 7x minus 18, I don't want that to be 0. That's in my denominator. But in my scratch work over here, I temporarily set it equal to 0 to find out when this happens, so I'll know how to prevent it from happening. So when I have this trinomial, I factor it. I believe this factors to x minus 9 and x plus 2. So I think if you substitute the value of x replace x with 9, 9 squared minus 7 times 9 minus 18 is going to be 0. And you won't get a corresponding y value. And for every number in the domain, you have to get exactly one y value. This number of 9, you won't get a y value, so we throw it out of the domain. Over here, x is equal to negative 2. So in my scratch work over here, I have equality, but what I really want is to say, don't let x be equal to those values. You know, what I really want is a not equal to. I really don't want that. So again, if I draw a number line. Now, rather than putting all the little tick marks in there, I know that negative numbers are over here on the left, that -2 is to the left of +9. And I'm excluding that value, so I don't want that to be a solid dot. But all these other numbers, they don't cause any problems. If you plug them in, you won't get a 0 in that denominator. So we say that the domain is the set of all real numbers, excluding these two values. Now, we have to be able to express that using interval notation. So D is for domain. Since we have three areas here to describe, this on the left with that arrow being shaded, that's -infinity. And we always have our smaller values, comma, larger values when we're writing our intervals. So we come up to from -infinity on the left all the way up, and it's increasing all the way to -2, but we don't include -2. Now, since there's a break in the graph, we need a symbol that's called a union symbol. In words, we read it as or. You're in this interval, or you're in this middle interval, or you're over here. So this middle interval is from -2 to +9, but it doesn't include those endpoints. Or you're to the right of 9, from 9 all the way, and that arrow is shaded all the way to +infinity. So there's the domain of this function written in interval notation. All right, so here we have two things going on. We have a variable in a denominator and a variable underneath the square root. So normally with just the square root, if I just had 1 minus x, then I would say, hey, 0's okay. I've got 1 minus x, and that has to represent a number that is either 0 or positive. But when I look here in the denominator, I need it to be strictly positive. I can take the square root of 0, I just can't divide by it. So this 1 minus x, I don't want to include this equality. I want to say it's strictly greater than 0 because it's in the denominator. If it wasn't in the denominator, I would have that equal sign there, and my domain would be different. So let's add x to both sides, and we've got 1 is greater than x. But like I said before, I like to write my variables on the left-hand side. The arrow always points to the smaller value, and it's pointing towards the x. And to say that 1 is bigger than x is logically the same thing as saying x is smaller than 1. All right, so like I say, the whole reason that I put it on the left is just so that it helps me when I graph it on a number line, get my picture straight. With x being less than 1, if this value represents 1, it's strictly less than, so this is going to be hollow, and less than is to the left, so I've got all of these values here to describe. And using interval notation, the domain of this is the set of real numbers from -infinity up to 1, but excluding 1. Alright, so here we have two functions, and they're using function notation, and they're giving these functions a name. They're not calling it Robert Morris maybe like I would, but it's calling it f and it's calling it g. This is a function f, this is the function g. And they're going to use these functions to create a new function. Now, rather than calling this new function h or something like that, they're naming it in such a way that it's telling us how we're building this new function. This f plus g is just notation saying, hey, if you add these two functions together, you'll get a new function, and it's called f plus g of x here. So all we need to do is to take this first function, 3 over x minus 4, and add to it this function g, 2x over x minus 2. So that's going to create a new function. Well, whenever we're adding fractions together, we've done it enough times in elementary school that we need a common denominator. Now, in algebra, oftentimes we just find a common denominator versus the least common denominator. And now it's a common technique in algebra to multiply by the number 1, but to be clever in how you write the number 1. See, 1 is the multiplicative identity. When you multiply by 1, you get the identical thing back. So here, we're going to write 1. Well, this first term is missing a factor of x minus 2 in the denominator. So If we have x minus 2 over x minus 2, that's just the number 1 in disguise. And over here, this next term has a factor of x minus 2 in the denominator. It's missing the x minus 4. So we write the number 1 as x minus 4 over x minus 4. That's how we're able to say that this statement, that these two terms being added together, is equivalent to these two terms being added together. Well, we can write this now as a single fraction rather than two fractions. Our denominator, x minus 4 times x minus 2. And you don't have to multiply that out. Most likely, remember that the final exam is going to be multiple choice. So you can look at the choices to determine whether they multiplied it out or not. I suspect that most of the time we would leave it in factored form because it's easy to see what the domain is. It's easy. You get information, a lot of easy information when it's in factored form versus when it's not. So here, though, I am going to have to distribute the 3 to the x minus 2 and get 3x minus 6. And I am going to have to distribute the 2x, and 2x times x is 2x squared, and minus 8x. So they will simplify that numerator. And most likely they'll write it with the exponents in descending order. This 2x squared will be the first term, and 3x take away 8x is a negative 5x. And then we have this constant minus 6. And like I say, most likely this is left in factored form, but just in case, since this problem is not multiple choice and we don't know what the answers would look like, we can say to look for this answer, or to look for, if I multiply this out, x squared minus 6x plus 8. Now, sometimes students are tempted to try to cancel terms, and you can't do that. Common terms do not cancel in a fraction, only common factors do. So be careful. You can't simplify this any further. So you're looking for choices that either look like this or like this. Alright, so it's the same idea here. We're given these same two functions. We're asked to create a new function. The name of this new function gives us a way to build the new function, and that's through subtraction. So we've got this 3 over x minus 4, and last time it was addition, and now this time it's subtraction. So once again, if you're adding or subtracting fractions, you need a common denominator. Multiplication and division is pretty easy, but when you're adding and subtracting fractions, it's a little more complicated. So again, we're going to multiply this by the number 1. The denominator is missing this factor of x minus 2. And over here, this term, its denominator is missing a factor of x minus 4. Now both of these terms have the same denominator, and we can express these two fractions as a single fraction. And we only have to do the operation of subtraction in the numerator. So again, I'm going to distribute the 3x minus 6. Now, when I'm subtracting here, I'm not just subtracting my first term or my favorite term. I'm subtracting this whole thing. So when I distribute this 2x, I've got 2x squared minus 8x. When you're subtracting that, you're subtracting the whole thing, not just a single term. So the parentheses are important, and sign errors are the enemy. We've got 3x minus 6 minus a 2x squared plus 8x. All that over this x minus 4 times the quantity x minus 2. So that numerator can be simplified, and we've got negative 2x squared plus, well, this time 8x plus 3x is 11x, and this time we have a minus 6 as my constant term. So we're looking for this as a possible selection in our choices of our answer, or if for some reason they did not leave the denominator in factored form, if they multiplied this out, we've seen that it's x squared minus 6x plus 8. Alright, so I hope that helps. Let's take a look now. Again, we're given the same two functions, and if we can build a new function through addition and subtraction, it makes sense that we can build a function through multiplication and division, and here we have division. So this new function, they could have called it h or q or p, or they could have given it any title, but they're helping us out in giving this f over g. They're telling us how to build this function. Now, if you have 3 over x minus 4, that's the function f, and that's in the numerator, and the denominator itself is a fraction. When you have a fraction within a fraction, they generally refer to this as a complex fraction. And so if students have an anxiety about fractions, they definitely have an anxiety about complex fractions. If I were doing this, I would not use the fraction bar here. I would write my numerator 3 over x minus 4, and then use the symbol here, this division symbol like this, rather than that fraction bar, because I think that's the easiest way for students to connect. I don't know in what grade they taught you that division was the same thing as multiplying by the reciprocal, that if you can change this to multiplication, if you flip that divisor, that second fraction, if we flip it and have x minus 2 over 2x. So, you can still get used to the fact of skipping this intermediate step and going from here straight to here, but I just think that it's a visual aid to write it out like that students are more comfortable with that. So to multiply fractions is pretty easy. You just multiply straight across the numerator and multiply straight across the denominator. This 3 gets distributed to both of those terms, so I've got 3x minus 6. This 2x gets distributed to both of those terms, so I have 2x squared minus 8x. And I can't simplify that any further. Now, of course, it's possible that they could have not multiplied that denominator. There is an advantage to leaving your denominators in factored form. And multiplication is what they refer to as commutative, that the order doesn't matter. We can write x minus 4 times 2x, or we can change the order of multiplication and write 2x times the quantity x minus 4. So you would be looking for this choice among the answers, or if they distribute it, like I said, 2x squared minus 8x. Alright, so it's going to be one of those two. Now, this is a new operation. You probably had never seen this before until you started studying functions, and I don't know how much time it was spent in Algebra 2. This operation, this hollow dot there, is called composition. Function composition. Now, the way that I describe function composition and stuff is to get students to think of an assembly line. It's a little bit awkward that you actually start with the second function. So remember when I said that functions are often thought of as a black box. So you have your input into the second function, g. So in this case, g takes whatever you give it and it creates this fraction. The numerator is 2 times the input, and the denominator is always the input minus 2. That'll result in some output, and that output now becomes the input for the function f. So that's why I refer to it as an assembly line. The order is important in function composition. So they want us to find an expression for this. So in g, we have an input of x, and the output of g, well, it's given right there, 2x over x minus 2. Now, the hard part is here in this last step, and that's to determine what the output is. So that's going to determine, me being a little bit more work for us. So you'll often see them write this as f of g of x. And this g of x, we can replace that, and we can say, well, you don't have to write g of x. It's equivalent to 2x over x minus 2. Now, let's come down here, finish down here. What does this f do to the input? Well, f always creates a fraction. 3 is always in the numerator, so 3 is still going to be in our numerator. Our denominator is the input, what's between the parentheses. Well, this time, what's between the parentheses is this ugly expression, 2x over x minus 2. And so what's in between the parentheses appears as the first term in the denominator. So we write this 2x over x minus 2 in the denominator. You see, what was between the parentheses here appears in the denominator as the first term. So this is in the parentheses here, this appears in the denominator as the first term, and then we subtract 4. Now, there's numerous ways that we can simplify this. Again, we have a complex fraction here. And this time, the easiest way to probably simplify this complex fraction is to actually multiply by the number 1. So we have to be clever in how we write the number 1. We're going to write that the numerator and denominator will be equal to each other, and they won't be 0 because 0 divided by 0 is undefined. I'm going to look to this denominator of x minus 2, and I'm going to write an x minus 2 here. So if x minus 2 is here, x minus 2 is there. Now, how am I going to multiply these two fractions together? Well, we had made the comment before that multiplication of fractions is not really all that difficult. You multiply straight across the numerator. So we're going to have 3 times this x minus 2. It's easy to see that that's going to be 3x minus 6. Now, here in the denominator, it is a little more difficult. This first term, this 2x over x minus 2, I need to take this x minus 2 and distribute it. Both of these terms get multiplied by this x minus 2. So this first term, it's going to get multiplied by x minus 2. To help me out a little bit, I'm going to write it over 1. That doesn't change the value of x minus 2. Then I have this subtraction, and I have this second number 4. Well, it also gets multiplied by x minus 2. This time I don't need to put it over 1 because that's just the value 4 there. Alright, so let's distribute in the numerator and get 3x minus 6. Here, hopefully you can see that x minus 2 divided by x minus 2, see, because this is multiplication, now I'm not canceling the individual x and then the negative 2. I can't cancel terms, but this factor of x minus 2 divided by x minus 2 is equal to 1. So what I'm left with in this first term, when I multiply these two together, is just 2x. Now, come over minus, and I'm going to distribute the 4 through there. So it's going to be a minus 4x, and then the negative times the negative there is positive. So I'm almost to my final answer. I've got 3x minus 6, and here 2x take away 4x is a negative 2x plus 8. Now, since those are terms, I can't come in and try to simplify this any further. For number 20, hey, this is my final answer. Alright, I'm going to stop there and continue the rest of Skill 3 in a different video. I've got some other things that I want to try and grade and get back to you. So I'm going to stop the video here and continue the other. I'll call this part 1 and continue in part 2 for the rest of Skill 3. Hope this helps.